Hi, this is problem number 69 in chapter 5 of the Giancoli textbook. It reads, because the Earth rotates once per day, the apparent acceleration of gravity at the equator is slightly less than it would be if the Earth didn't rotate. Estimate the magnitude of this effect and what fraction of g is this. I've made a quick sketch over here where we know the radius of the Earth that's given to you at various points in the text. And so let's go ahead and make a sketch, in this case of a free body diagram. We've got a couple of different forces acting on this guy. We've got the center-seeking gravitational force, which we can call weight, and we also have a slightly smaller normal force, and that's going to produce kind of this leftover center-seeking centripetal force, or what we can call a net force. In this particular problem, I can write the equation out and say that the sum of the forces is going to produce this leftover force. So therefore, establishing a coordinate system saying that center-seeking is positive and radially outward would be negative in this case, or to the right is negative and to the left is positive, I get F sub c is equal to mg minus F sub n. And writing out F sub c, breaking it up into its constituent parts, I get mv squared over r sub e, where r is the radius of the Earth, is equal to mg minus F sub n. I can realize here that if this were moving in a straight line, that the normal force would be equal to mg. At the end of the day, the normal force here is the experience of weight, the Earth usually pushing up on you with your weight mg. So let's go ahead and rewrite this equation in terms of the normal force. So I'm going to add the normal force and bring this term over here, and I basically get F sub n, or the normal force, is equal to mg minus mv squared over re. And I can factor out this mass, and I get the normal force is equal to m times g minus v squared over re. I again draw your attention to this term here, v squared over re. Notice that the normal force, or your experience of weight, is going to be equal to mg normally if there is no circular motion. But since you are rotating around the equator, we then need to subtract this piece over here, v squared over r. This ultimately becomes your delta g, if you will, or the change in the gravitational acceleration. Let's go ahead and solve this for v squared over re. Again, if what's in purple isn't here, then the normal force, or your weight, is equal to mg, and your acceleration is equal to g. So this is pretty straightforward until you introduce this circular motion portion that I've circled in purple. So therefore, this change in gravitational acceleration is going to be equal to negative v squared over re. In other words, the change is going to make the acceleration smaller than it actually is. It's going to be slightly less than 9.81 meters per second per second. Putting this in, I need a value for my speed, and I should recognize that this is going to be 2 pi r sub e, which is the circumference around the Earth, 2 pi r, over the period, or the amount of time that it takes to go around the Earth, and all of that's going to be squared. Of course, that's all over r sub e. So now I can see, that I'm going to get something that looks on the order of this. It's going to be basically 4 pi squared r sub e squared over the period squared all over r sub e. And I can see that this here on the bottom cancels out with one of these here. And so finally my expression for my change, which of course is negative, I've omitted that to carry that negative sign into these subsequent terms, becomes negative 4 pi squared r sub e all over t squared. Okay, so this expression right here is ultimately what I'm solving for, I should also recognize that when let me turn this on and pan down the page a little bit, I should recognize that the period is the amount of time that it takes to complete one rotation. Of course, that's 24 hours, but if I convert that to seconds, it's 86,400. And I need to convert the radius of the Earth, which is given to me as 6,380 kilometers, to meters. So plugging all of these things in here, I get delta G is equal to negative 4 pi squared times the radius of the Earth, which is going to be 6.38 times 10 to the 6th meters, once I convert that to meters, all over 86,400 seconds. And of course I need to square that as well. Okay, plugging all of these numbers in, I'm going to get something very small, negative 0.03374 meters per second per second. So we can see that the delta is quite small. I can convert this to a some fraction of g by multiplying this number by 1g over 9.8 meters per second squared. So therefore, as a fraction of g, I can say that negative 0.03374 meters per second squared, and I'm going to multiply that by this conversion factor where 1g is equal to 9.8 meters per second per second. Alright, when I do that, I get basically negative 3.44 times 10 to the negative 3 G's. And that would be the answer to the kind of second part of this, which is express this answer in terms of G.